Yeah. We can probably start saying just some filler words. Welcome. We're very happy to have more people joining for this edition of Gauge Theory Virtual. We've got Ian speaking today, probably something like link surgery formula and plumbed manifolds, if I'm reading the title. I guess I will let Ian take it away. Thank you, Ian.
Okay, thank you for the introduction. Thanks everyone for coming. It's nice to be here virtually talking about this. So today we're going to talk about Higord-Floer homology and plumbed manifolds and lattice homology. So the objects are of interest. The topological objects of interest are plumbed manifolds. Many people probably know what these are, but just to kind of do a really brief review. What is this construction? Well, what we do is we take D2 bundles over a surface. Let's say we take one and let's call it F. Or sorry, let's say X, sorry. X over a surface F. And what I'm going to do, let's say here's F, here's X. What I'd like to do is just pick 2 points in this D2 bundle and trivialize a neighborhood over these points. So P1 and P2, these will have neighborhoods of the form D2 times D2. Let me write that, trivialize neighborhood. Trivialize, I guess neighborhoods, what are P1? P1 and P2 are points in the base, yeah, which is a surface. Let's say oriented, I mean, it doesn't, let's say it's an oriented surface F. I mean, we will restrict to the case where F is just a collection of spheres, but what we're gonna do is we're gonna trivialize neighborhoods of P1 and P2. So the neighborhood of P1 and P2 in the base is just a disk. And we can trivialize it, it's a disk bundle, so we can trivialize each neighborhood as D1 times D2. Let me draw this a little better. And what I'm going to do is I'm just going to glue, I'm going to form a new 4 manifold, which I'll call X tilde. And what I'm going to do is I'm just going to glue D2, the 2 copies of D2 to each other, but I'm going to switch the role of I'm going to switch the factors or swap the factors. And so this will give me another manifold, which I can maybe draw like this. So that gives me a 4 manifold, X tilde. And really, I'm interested in sort of the boundary of this manifold. So we're interested in the boundary of X tilde. The boundary of X tilde. And of course, you could also kind of do this many times. You could take, you could do this, we could repeat this operation. Of course, can repeat for any collection. You know, we can repeat this operation if we have a collection of pairs of points. We have many pairs of points. In F. And so what I'm actually, the case that we're kind of going to be most focused on is that F is a disjoint union of spheres. Of 2 spheres. And what I want to do is I want to plumb according to a tree. Okay, so in this case, we can encode a plumbing by a tree. a weighted tree. In this case, a plumbing is encoded by a weighted tree. Well, a weighted graph. And in this case, I'm actually going to, let me say a weighted graph. And I'm going to actually restrict to the case where the graph is a tree. And we can restrict further to the case that it's a tree. But what this looks like is we'll have a graph that maybe looks like this. I mean, topologically, you don't have to restrict to the case that it's a tree, but we're going to focus on the case that it's a tree. And so I have a graph, so I have vertices and edges. And so let's say this is my, my graph. Okay, and so the recipe for constructing this is we have one D2, we have kind of one D2 bundle over S2 for each vertex. The weight is the Euler number. And I have an edge if I an edge for if I for each time I plumb. So given an edge, I'll plumb the corresponding S2s together, or the corresponding disk bundles over S2 together. And I just do this according to the edges, and I get some, you know, if this graph or tree is G, I get some 4-manifold XG. And the 3 manifolds of interest are kind of the boundaries of these. So I'm going to write YG as kind of the boundary of this 4-manifold XG. And I guess this is 10x3. Okay, and so there's another description which is important, which is surgery on a link. Which is surgery, let's say just Dane surgery on a link. Let's say LG in S3. And this link LG is a connected sum of Hotflinks. And basically, for every vertex, you have one unknotted component. And for every edge of my tree, I'm going to have one clash. So maybe I can attempt to draw this guy for this example. Oops. Let's see. So I'll have one component here. And maybe one here, one here, one here, and one here. And so this is a connected sum of Hotflinks. It's this could be LG, and the framing, it's a framed link. The framing is just the weights. So I just take the weights and I just give it that integral framing, -1, so I'm just copying it from above. So this is a 2. This is 2, this is 3, this is -5. Okay, any questions on any of that? Okay, so what we're interested in is the Haggard-Floer homology of such three manifolds. These are plumbed three manifolds along a tree, where the bases are S2s. So there's a combinatorial theory for such. There's a combinatorial invariant for such manifolds called lattice homology. Oops. And this is due to Nemeth. I'm sort of inspired by Oshvath and Szabo's computation of Haggard-Floer homology for some plumbed three manifolds, as well as some algebraic geometric, some imports from, or some considerations from algebraic geometry. So he kind of combined their computation for some plumbed three manifolds with some insight from algebraic geometry. And what he came up with is this combinatorial theory, a combinatorial invariant of plumbed three manifolds. So combinatorial invariant of plumbed three manifolds. So I'll review the definition, or one of the ways to define that. I'll review that here so people can get a flavor of it. But to one of these weighted trees, there's an invariant which I'll call CFG, and it's a chain complex. And the homology I'll denote HFG. And so one of the things Nemeth proved is that this is an invariant of the three manifold YG, i.e. it doesn't depend on doesn't depend on the graph G. There's Kirby moves. I guess usually you call these Neumann moves between two different plumbing trees that represent plumbed manifold, and it's invariant under these moves. So it's invariant under certain Kirby calculus moves. It depends only on the three manifold YG. I'll recall the definition just briefly so that people can get a kind of sense of what this looks like. And I'm actually going to use so I'll give an overview using the notation of another group, Oshvath, Stipchitz, and Szabo.
Are we assuming that the graph is negative definite?
Right, so Nemeth defined it requiring the graph is negative definite, but the construction of Oshvath, Stipchitz, and Szabo doesn't require that. So yeah, so that's right. Nemeth's original construction did require the graph to be negative definite. I think, yeah. But the other formulations don't. I think that was more just kind of like a superficial thing. I can't remember Nemeth's notation. Definitely the Oshvath, Stipchitz, Szabo approach does not require that. And so what we do is we look at these. We look at what characteristic vectors on the four manifold. On this four manifold XG. Of course, these are familiar objects in gauge theory. These are elements of H⁻² that satisfy Kx minus, or maybe X isn't the best letter. Let's say K sigma minus sigma dot sigma is congruent to 0 mod 2. For all elements in H⁻². And so these are familiar objects from gauge theory because they're basically the set of Chern classes of spin C structures. So they of course, many people these appear all the time, and we use them to build the generators of this lattice complex. So CFG is generated. Oops, it's generated. Sorry, by kind of formal tuples of the following form. We say bracket KE, so just kind of a formal symbol KE, tensor U to the I, where K is a characteristic vector. E is some subset of the vertices, so the vertex set, and I is some positive, or not, sorry, non-negative integer. So they're just kind of these formal tuples, K, E, and then you have a power of U. And so as Matt said, there are some subtleties that, if you are, for non-negative definite things. And in this case, basically what you need to do is, if you don't work with something that's negative definite, technically you'll need to work with some completions. So technically, if it's not negative definite, you'll need to work with basically the direct products over K comma E of these guys, K, E, and you work with power series rings. But kind of formally, it's the same thing. There's some issues with completions. You have to, let me actually rewrite this. So technically, these aren't the generators. The generators are kind of in this completed thing, but that's, conceptually, it's not, one doesn't have to, it doesn't add a lot of complication. So direct products and power series, right. And so the differential, I'll kind of give you a flavor of what this looks like. I won't tell you all the formulas involved in it, but if I take one of these pairs KE, the differential is roughly, there's kind of two sums in here. There's two kind of there's two terms of the differential corresponding to two ways of deleting a vertex from E. In each term, we're going to delete one vertex from V. So we're going to sum over the vertices in E, which are the ones we're going to delete. And the first term, we just delete. We don't change K, and we just delete V, and then we need to multiply by some power of U, which I won't tell you what that is. But there's some, some power of U, you multiply. But basically, one way of deleting the vertex, you just kind of delete it and don't do anything. And there's some power of U you need to multiply by, but you won't tell you what that is. And the other way is a little bit more complicated. Instead, you also have to change the K, the characteristic vector. And you do that by adding 2V star, where V star is basically the Poincare dual of the vertex. So the vertex, corresponds to a two-sphere on this manifold XG. XG has a description as surgery on this link, so you can kind of take the core of the two-handle corresponding to the vertex, or to the knot component corresponding to the vertex, and you get a two-sphere, and V star is the Poincare dual of that two-sphere.
So, Ian?
Yeah.
Sorry, I'm just confused by taking the Poincare dual at that point, because that should be a relative class. Does it matter, or don't we care?
But it's good question. Okay, so right, so we have our manifold here, or let's say it has two components. So sometimes these things get in this case we'll just cap it with a little disk in S3. So good point. So we have YG here. Let's say this is XG, and then on one boundary, oops. I'm saying it's surgery on some link in S3. So technically, you know, maybe you have an S3 boundary component with this perspective. And so this.
I guess I was worried about the sort of the other end. Oh, okay.
Right, it's the core of, not the co-core, but the core of the two handle. Right,
Okay.
the co-core would have a boundary, and you're right. You might not be able to cap it if it was the co-core of the two handle, but kind of I cap it in S3 with one. Right.
Okay. Thanks.
And then you multiply. Okay, so we have these two terms, and we multiply this by some power of u, which we won't talk about. Okay, any questions? Great, okay. So, I mean, lattice homology is basically inspired by Heegard-Floer homology and is, you know, I mean, it's also inspired, I think Nemethy was also largely inspired by algebraic geometry, but one of the main sort of motivations for lattice homology was trying to compute the Heegard-Floer homology of three manifolds, plumbed three manifolds. And so there's a long history of results relating Heegard-Floer homology and plumbed three manifolds. Heegard-Floer homology and lattice homology. So in many cases, there is an isomorphism. No, the isomorphism is known. It's YG is isomorphic to HF minus the Heegard-Floer homology groups of Ostwald and Szabo. This is known in many cases. Most of the cases focused on negative definite graphs. I mean, that was the original setting, was negative definite graphs, where this four manifold XG is negative definite. In that case, there's certain technical aspects of the definition which are easier to work with for negative definite manifold. But kind of the original setting, I guess, the original result is kind of Ostwald and Szabo's original computation. So these are, let's say, these are the case where G is negative definite and at most one bad vertex, at most one sort of bad vertex. And what is a bad vertex? That's a vertex where the weight, well, the weight has to be a negative number. But if the weight is not negative enough, it's called a bad vertex. So the degree, the valence of the vertex. So a bad vertex is one where the weight is not less than minus the degree of the vertex. So kind of if all the weights are really negative, then you know this isomorphism holds. But Ostwald and Szabo also proved that if there's one vertex where the weight isn't sufficiently negative, but all the other ones are sufficiently negative, then basically the isomorphism holds. Of course, their result wasn't stated in terms of lattice homology because their result predates the definition as the formalization in terms of this homology theory, but it is kind of the, basically their result proves it in this case. And so Nemethy kind of generalized this to another setting, which is what he calls almost rational graphs. Basically, if you have a negative definite graph G, this YG is actually the boundary of a normal surface singularity from algebraic geometry. And there's this sort of there's this family of singularities called the rational singularities, and these are sort of the simplest singularities you could look at. There's I'm not going to get into the algebraic geometry, but they're like sort of the simplest ones you could do. You could look at. It's an Nemethy proof that almost rational graphs satisfy this isomorphism where almost rational means changing one vertex changing the weight at one vertex gives gives a rational graph. And so Nemeth also proved kind of another perspective on rational graphs, which he also proved that, so assuming G is negative definite, then G is rational if and only if YG is an L space. Which is that, i.e. that the Hilbert-Floer homology of YG is as simple as possible. It's just a direct sum of some number of F adjoin U. It's the simplest possible module that it could be. And so kind of Nemeth's results in this direction are, saying that kind of rational graphs, when it's negative definite, these give the simplest possible Hilbert-Floer homology. Like in some way, it's being rational is as simple as you could, but also this isomorphism holds. In addition, if it's almost rational, if it's kind of close to being rational in some sense. And although this is like a fairly restrictive condition, if you write down like weights on a graph, topologically it's fairly general. So every fiber homology 3 spheres satisfy this, for example.
So that's not my feedback. Sabo showed that if you have no bad vertices and it's an L space, and like is this like, are there examples then of rational? Do you have like a simple example of a rational graph that's sort of has multiple bad vertices or any bad vertices? Like is the first Nemeth result on this page, is that strictly greater, sort of wider class of manifolds than what Osvat and Sabo proved it for?
Oh, did they prove that they were lens spaces?
No, they proved that they were L spaces. There were no bad vertices, and then they sort of extended it to one bad vertex, kind of like that's where the induction stopped. And I was just wondering, like, does Nemeth get sort of larger classes of L spaces and correspondingly the larger classes of manifolds for which he could compute?
Well, he showed it was an if and only if statement. Like the rational state, the fact that it's a rational graph has some.
Can we, Junyan? I think can you mute yourself, please? Thank you.
Right. Is it? What was the?
So I think.
Sorry. I mean, so Nemeth originally proved that lattice homology of a graph was, in his original work, he proved that lattice homology, like the lattice homology was, looked like that of an L space if and only if the graph was rational. But it wasn't known whether these were the same thing and whether Hilbert-Floer homology was the same. And so I guess I guess the point is that there's no more L spaces. Like the Nemeth's more recent result, this last one, is that there's no more L spaces in.
Right. So I guess my question is, like, is that class then exactly the class of negative definite plumbings, on trees with no bad vertices? Like that's certainly a subset of the L space ones. Not the same. So what's like? Okay.
I think the E8 plumbing is rational, but it has one bad vertex, and you can't write it as a 0 bad vertex plumbing.
Okay. That's it. Okay.
Thanks, John. Yeah. Yeah.
Is it known sort of how, like, is a sort of distinction classified or well understood? Like, sort of what?
I don't know the information about, what.
Okay.
I mean, there's a description of rational graphs that's combinatorial due to Barton.
Okay.
But I don't remember like the relation. I don't know if and only if in terms of like bad vertices.
Yeah, thanks.
Okay, great. Anyway, so these are kind of some greatest hits. There's also another good one. I mean, another sort of important result that we're going to talk about, or that we're going to use, is the result from Ojva, Stipschitz, and Szabo, which is type 2, or I guess almost rational graphs. Type 2, right? 2 vertices can be changed to get rational. be changed to get a rational graph. And they showed that the isomorphism in this case. And actually, more generally, what they showed was that there's a spectral sequence from YG to Higard-Floer homology. So that gives you kind of, some relation between them and some sort of rank inequality. And the way they used this was using this Manifolds-Oshvat link surgery formula. And so this is kind of the approach. This last approach by Oshvat, Stipchitz, and Szabo is kind of the one that we expand on, that I expanded on to, or investigated further. And so kind of finally the result is just that you kind of building on all of these works, I've proved this isomorphism holds in general. And I'll tell you the main points of the proof, or I'll try to tell you the main points of the proof. But that's kind of where we're going. So I guess for all trees G. So I don't assume negative definite. And the point was that basically we go through the link surgery formula, which doesn't really need, it works for any framing. It doesn't require negative definite. Okay, any questions on that? So kind of building off of this, the work by Oshvat, Stipchitz, and Szabo, kind of their approach to proving the spectral sequence was to study the Manifolds-Oshvat link surgery formula. And so that's what I did as well. I kind of expanded on the work of Oshvat, Stipchitz, and Szabo. And so the main tool is this link surgery formula. And so what this does is that if you have a link L in S3 with some framing lambda, what this gives you is a chain complex C lambda L, which computes the Higard-Floer homology of the surgery. And, I guess that on its own is maybe not that interesting because kind of you already have a chain complex that computes the Higard-Floer homology, but the kind of the importance of this formula is that it's a useful tool for actually doing computations. And that's because it's built from the link Floer homology of L. It's built from the link Floer homology of L. So, and so kind of the generators of this complex are easy to understand, but in general, the challenge of doing computations is understanding the differential in the complex. This is a, eternal struggle of gauge theory is that we can't really, it's hard to actually compute, it's monopoles, or it's hard to compute pseudo-holomorphic curves, but it does give you a lot of kind of structural insight just knowing that there is a chain complex with this underlying group. And so the structure of, I'll give you like a brief overview of the structure. So if I take an L component link, then this chain complex C lambda L is what we call an L dimensional hypercube of chain complexes. And so concretely, that just means that you have some filtration by the cube. And so if I took if L is 1, then I have a one-dimensional cube of chain complexes, which means that the differential kind of looks like this. I have kind of, two chain complexes, C0 and C1, which have some internal differentials. And then this, link surgery formula is a mapping cone from C0 to C1. So I have some differentials going from C0 to C1, and then I have internal differentials. If L is 2, then I get this kind of cube-shaped chain complex. C01, C10, C11. And so kind of the arrows in the chain complex can never decrease the cube filtration. That's basically all a hypercube is. And hypercube basically is just del, the relations are just del squared equals 0, where del is the sum of all arrows in the picture. And so of course L equals 3 is kind of a 3-dimensional cube. That's kind of the structural shape of the link surgery formula. And so the underlying group is usually pretty easy to understand for this link surgery formula. So if I write this as follows, I'll write it as C epsilon D epsilon epsilon prime, where epsilon are points in this cube. Actually, this group, let me just focus on the 0, the kind of initial point of the cube, C0. This is actually just isomorphic to just link Floer homology itself of L, where this is the kind of version of link Floer homology, which is free over F you want kind of a two L variable, some polynomial ring in 2 L variables. So it's actually just the link Floer homology, kind of in a particular version, which is a free module over some polynomial ring. And the rest of the C epsilons are just localizations. These are actually just localizations of this group here over by some of the V variables. By some of the V variables. So I have the U's and the V's, and it's a localization of some of the V's. And the differential, the internal differentials, so D epsilon epsilon, so I don't increase the cube filtration at all. These are just the ordinary Haggard-Floer differentials. Or sorry, link Floer differentials. Floer differentials. So in particular, in the case of a plumbed manifold, LG is a connected sum of Hotflinks. Well, I can just use the ordinary tensor product formula for link Floer homology. And basically this group, the C epsilon, these are easy to understand using the normal connected sum formula. The groups and the internal differentials, these are just kind of the, these are just easy to write down. There's nothing necessary to understand. But what's hard is to understand are the hypercube maps. Let me write it this way. So the challenge, kind of the remaining challenge, is to understand the D epsilon epsilon prime, these maps in the cube, which kind of move farther in the cube when epsilon is less than epsilon prime. And these are going to involve, holomorphic polygon counts of, pretty high, a large number of holomorphic polygons. So in practice, even writing down a diagram for a simple link it's challenging to just compute by hand, even for the simplest of links. Let me say, involve many holomorphic polygons. For instance, the Hotflink, at one point, I tried to write down all of the holomorphic curves which contribute to it. And, it was actually quite challenging to write them all down by hand. Even for the simplest of links, it's pretty hard to compute by hand any of the holomorphic polygons contributing to the differential. You can compute, yeah, go ahead, sorry.
Yeah, I'm sorry, can I ask a question about C0? Are you doing some kind of simplification of Maneliscu-Oshvat's original picture, or like, because I had always interpreted that as like we're really taking like, you know, a direct sum over all the different like sort of subcomplexes in the filtration.
That's right. So they have a different description of what C0 is, but it turns out to be exactly this. So the way to understand it is that Manolescu-Ojva, their definition is that C0 is equal to a direct sum over, yes, actually, let me do the ordinary mapping cone formula, because for Ojva and Zaba, because once you understand that, the rest is like just, you go from knots to links and there's no, so let's actually do the simplest thing, which is let's do the Ojva-Szabo mapping cone formula. This is a good point though. So let's just, I mean, this is important. I mean, to actually do anything with it, it's important. Maybe conceptually, I shouldn't emphasize it, but it's an interesting point. So, you know, their A, which is sort of like the C0 in the Manolescu-Ojva notation, their A is, I guess you would say, direct product over A sub S, where S is in Z. But actually, A sub S is identified as a subcomplex of this not Floer complex. This is the subcomplex in Alexander grading S. You know, it's so you can I mean, they usually describe it as part of CFK infinity lying above some Alexander filtration, but like there sort of is this alternate perspective where you have an Alexander grading on this kind of free complex over F adjoin UV. And so when you take the direct product over the A sub S, you just get the not Floer complex, CFK of K. And it's similar for the link Floer setting, because they're taking this direct product, but if you translate it, it's just taking the direct product over all Alexander gradings of this link Floer complex. So of course you just recover the actual link Floer complex. And actually doing computations, it's easier to work with this perspective of just the, I mean, because the link Floer complex, if you work over 2L variables, is finitely generated, whereas their description is this quite large, infinitely generated complex.
Yeah, thanks. That's helpful.
And so kind of the okay, so the strategy, I guess there's kind of two I guess, you know, the goal is just to compute. Okay, so what would a strategy be? Let's see, what do I want to say? So here's the strategy is, you know, we compute C lambda H for the Hotflink. And that's kind of the first step. I mean, and that's not that intense, but and the second step is to prove a tensor product formula. And there's a few, I mean, so there's a few more steps that actually end up happening. Like this story is somewhat complicated, but these are the main ideas. Is you compute it for the Hotflink, and then you prove a tensor product formula for it. And so for the Hotflink, actually most of the maps are just uniquely for the Hotflink. Most maps are determined by grading considerations. The only one that isn't is actually the length 2 map, which has sort of 2 valid choices up to homotopy. And that is some source of consternation, I guess. The length 2 map has 2 algebraic choices. As I mentioned, it's pretty hard to actually compute holomorphic polygons. I mean, one could presumably do it, For this case, because the holomorphic polygons, I mean, presumably one could, but it actually in practice is fairly tedious to actually do that, even for the Hotflink. And so it's much easier to just work algebraically and look at the constraints of the various maps in terms of gradings and filtrations, and just, it turns out basically there's two sort of models for the Hotflink algebraically, and one has to do some other argument to decide, one needs to kind of have some other argument for which one is valid. Maybe we'll return to that in a moment. But it turns out there is actually one that is the right choice. And from the perspective of Manolescu and Oshva, there's and there's there's some tricks that you can use to determine which one is the right choice. We'll return a bit to that in a moment. But the other point is that one needs to prove a connected sum formula. For the link surgery, formula. And so what this is the way that we're going to phrase this is we have kind of two, we'll have to take L and L prime are framed links. Let's just say S3, and we take kind of two special components. And what I'm going to do is I'm going to ignore a lot of the directions in the cube. And so I can write C lambda L as a mapping cone. If I just forget many of the directions in the cube, I can write it as a one-dimensional mapping cone that looks like this. Oh, sorry, C1. Okay, and so what does this mean? Well, this is an L-dimensional cube. And I'm saying that this is what, it's an L-dimensional cube. And so what these terms are is these are L-1 dimensional cubes. And what they correspond to is they correspond to all of the parts of the original cube where the component, the index corresponding to k is 0 or is equal to 1, right? So like the 0 term here, this guy is all the points in the cube where the index for k is 0. And this one is the part of the cube where all of the indices for k are 1. And the Manolescu-Oshva formula, it's kind of each of the maps in the hypercube is associated to an oriented sublink of L. And so for the maps going from the 0 index to the 1 index for k, I can decompose those all. I can decompose those as a sum of two maps, phi plus and phi minus. And so the plus ones are kind of for all the sublinks which contain k positively oriented, and the minus corresponds to all the components, all the sublinks of L which contain k negatively oriented. And so this is just a structural form of their hypercube to say that it decomposes as a, that you can decompose it this way. But of course I could do the same thing for L prime. I could write it kind of as a cone over in the same manner, but over, decomposing over the special component k prime. And I could write it like this. And basically, there's really only, you would probably guess that there's, sort of there's only really one way to amalgamate the symbols to get a guess for what, the hypercube for the tensor product would look like. And that turns out to basically be the right answer. So kind of the key connected sum formula is that if I take the connected sum of two links, on the special components, K and K prime, I'm just going to sum their framings. And on all the other components, I don't do anything. I just take the framing from L or L prime. And so this has a decomposition, which is as the mapping cone of C0 lambda L tensor C0 lambda prime L prime to C1 lambda L tensor C1 lambda prime L prime. And the maps are just the tensor products. I tensor the plus maps together, and I tensor the minus maps together. And if one stares at this, it is possible to interpret this as an A infinity tensor product over some algebra. Probably I won't talk too much about that, but you can interpret this as sort of an A infinity pairing if you stare at it long enough. But that's not really necessary just to get to this isomorphism between lattice homology and Hilbert-Floer homology. And so there's kind of one. So this is kind of the connected sum formula. And so how do we put the pieces together? Like, where does this? What is kind of the main idea of this isomorphism? I'll say a little bit about this and I'll probably wrap up. So the Hotflink complex so how does one put all these pieces together? So the Hotflink complex, just the link Floer complex, not the link surgery formula, just like the ordinary, it is this really simple diagram that looks like this. It is this quadruply based diagram with just one alpha and one beta, and it's on the two sphere. So it has this Hilbert diagram that's really simple. And if you write down the complex, it's quite simple. It's just U1, V1, U2, V2. It's very simple, but in particular, it has this two-step filtration. It has this two-step filtration. And so you kind of have, this is like, let's say, A and D, and this is maybe B and C. And basically the homology, if you take homology of this complex, it's supported in H0. I realize I've forgotten to say something important. I've forgotten to say, there's something I wanted to say. Yeah, so what is the, so I think actually instead of going to the Hotflink, I want to just say something more basic and finish on that. And so I want to actually just touch in on Ojvath-Sipchit-Szabo's result. And what is the relation? Maybe I'll just continue with the Hotflink. I'll just stick with what I was doing. So the Hotflink complex looks like this. And so in particular, the homology is supported in H0. And so what you can do is if you look at the link surgery formula, if you look at the link surgery formula, C0, let's say for LG, which is a connected sum of Hotflinks. So this is a connected sum of many copies of the Hotflink complex. I guess I called it H. Maybe not C0. Yeah, C0. It's a tensor product of copies of H, this Hotflink complex. And so in particular, and so C epsilon is a localization. Each C epsilon is a localization of C0. But this actually means that C0 and actually each C epsilon, focusing on this link LG, it actually has a filtration. It has, or a description as, let's say CL epsilon to CL minus 1 epsilon through C epsilon 0. And the homology, and actually it's a result of Oshvath and Stipchitz, or let's say it's a fact used by Oshvath, Stipchitz, and Szabo. If you translate it, that actually the homology, if you think about it, the homology is torsion-free over F adjoint U. And so in particular, there's each of these complexes, C epsilon, are actually just free resolutions of their homology. Because the homology is supported at the lowest grading in this lowest filtration level of this complex. And so what Oshvath, Stipchitz, and Szabo actually do, they give a description of lattice homology. They actually relate, maybe I'll end on this because I'm running a bit out of time, but they relate lattice homology. They state a partial relation between lattice homology. They prove a relation. In the link surgery formula. And so what they do is they look at this hypercube D, C epsilon, D epsilon, epsilon prime of this link LG, and they construct another hypercube. They construct another hypercube. And so this hypercube is as follows. Another hypercube. And what they do is they look at, I'll call it H epsilon delta epsilon epsilon prime, and H epsilon is equal to the homology of C epsilon. And delta epsilon epsilon prime is equal to the induced map for the length 1 maps. It's the map induced on homology by the length 1 maps, or 0 if epsilon prime minus epsilon is greater than 1. So what they do is they construct a cube by taking homology of the link surgery formula, the homology of the complex in the link surgery formula at each epsilon, and then the length 1, and then they define cube maps, which are just the induced maps on homology for the length 1 arrows and then they forget all of the higher arrows. And what they prove is that actually this hypercube is just equal to the lattice complex. And so if you take the length surgery formula and you take homology at each vertex and you only remember the length 1 arrows of the cube, that is the lattice complex. And so basically what my proof goes is the way this works is that I guess, you know, you kind of, I prove this connected sum formula. And then what you can do is you can actually define a map. I guess I've run out of time. I think maybe I'll just end with saying that with like, so you can basically, maybe I'll just end with a little bit of vagary and then I can tell people more if they want to stick around. But using the connected sum formula, you know, one can show, one can basically define a quasi-isomorphism. A quasi-iso from this this complex C lambda LG to this kind of reduced module, and that was this lattice complex directly. And so, and that's kind of some homological algebra and a few other steps. But I think that's all I want to say because I know people are busy, and so people want to know more. They can stick around and ask a few questions.
All right, well, thank you, Ian. Are there any questions for Ian?
So can you elaborate on the last part?
Yeah, so yeah, sorry. So sorry for going a little over. So the idea is
before you elaborate, can you also say what is the difference? So you said that you identify the homology of the first page with the lattice complex, and the differential is the obvious one.
The differential is the obvious one, but the point is that I guess that the thing is that you can define a map, and the way that you can define a map is as follows. So at each C epsilon, so we can write C epsilon as this kind of chain complex like this, using the filtration or the kind of decomposition as a Hotflink complex. You know, the Hotflink has this very simple, it has these kind of two steps to it, and you have a map that goes from 2 of the generators to the other 2. It's a very simple chain complex. So when you tensor many of them together, it still has this structure, except now you have L steps. It's you kind of have this additional grading, but since the homology is actually all supported in the bottom grading, there's actually a surjection onto this group H epsilon. Basically, it's just a free resolution of its homology. You know, each of these C epsilons, it's a free resolution over, let's say, so C epsilon is a free resolution over H epsilon, of H epsilon over this ring here, F adjoint U. And so let's just, maybe the easiest thing one could do is just define a chain map from the link surgery formula to the Hotflink complex. And so what you want to do using the connected sum formula is you actually just want to do something very concrete for the Hotflink. So what one needs to do is construct a model for the Hotflink. For the Hotflink, where the arrows, so we had the Hotflink was like H0 to H1. We need all of the arrows to not move forward in the complex. So we have this filtration, and basically we need no arrows to move from I guess I'd put it backwards. So H1 to H0. So you can have basically, I need all of the link surgery maps to either preserve this grading or increase the grading. Because if you think about that, when you tensor all of these together, that'll mean that the map that you get by just projecting each C epsilon to H epsilon is a chain map. Like the thing that would happen that could mess up this map being a chain map is you could have, think about, maybe you could have something from C1, you take the differential of it, it goes to C0, and then you project, and that might not be the same as projecting and then taking the differential on the lattice complex. And so basically after you've proven this connected sum formula, it becomes a pretty concrete computation involving the Hotflink. That the goal is basically you need to construct this model of the Hotflink that has this filtration property to the maps.
I see. Thank you. Another question, in the connected sum formula, what is the A-infinity algebra?
Yeah, so there's actually an algebra that you can view. Right, so there's an algebra that one can work with. And this is basically what you want to do is you can define this algebra K. I define this algebra K, and it's somewhat of a long story, but there's two idempotents in this algebra. And what you can do is you can define, so the flavor of this algebra, there's some algebra K, and basically it has these two idempotents. And I1, K, so you have idempotents I0 and I1. And so this is like in idempotent I1, you have F adjoin UV, V inverse. And then in idempotent, and then you kind of have some arrows that go from idempotent 0 to idempotent 1. And there's these two special elements, which are, I call them sigma and tau. And basically tau sigma commutes with, there's some relations between, there's a multiplication on this algebra, which is easy to identify. But basically what I proved is that this link surgery formula, there's C lambda LG, basically has the same information, or just repackaged, you can think of it as a type D module over the tensor products of L copies of this algebra. Right, so K kind of corresponds to a link component, and you can think of this as a type D module over this algebra. And there's another, there's a module that kind of merges two components together. That's kind of a DA bimodule, I guess, using this like Lipschitz, Oshvat, Szabo notation. And basically what you can think of, so let's say this is like C, or let's say not LG, but we could call this C lambda L. Basically, you could think of this pairing theorem is a tensor product. I'm going to call this algebra L. L, and then you can tensor, basically you take an external tensor product of, like you just tensor them over F, and then you get type D module over kind of the tensor product of the algebras, L tensor L prime. And then this is, you kind of just input, there's a box tensor product with this other module, where you kind of input the special components into some third module. And this is the kind of type D module over the tensor product. L double prime. There's some way of writing down a tensor product. And the tensor product is pretty simple. Like as a vector space, it's just the idempotent ring. And basically what it says is like you take the two, like basically what this merge module is it's like you take tau tensor 1 and 1 tensor, it has a delta 3 1, where you allow kind of 3 inputs and kind of, and then maybe idempotent 0, and kind of these go into a delta 3 1, and then the output is like a tau on the outside, which basically says this is just the way of saying that like you obtain the hypercube maps by tensoring. I mean, that's all it's saying. And so there's some A infinity way to describe things.
Is there a topological way of describing what MK is? Is it like something?
I mean, it's just an algebraic thing. I think if you set up the whole theory, like kind of tautologically, it'll be the thing for a pair of pants, like S1 times a pair of pants. But it's, I mean, that kind of probably like what you would do is you say that a 3 manifold with torus boundary components gives you a type D module, and then to get a type A one, you just tensor with this module because it switches a type D component to a type A component. And then probably tautologically, the pair of pants one is just has this bimodule. Right.
Quotient by like setting U and V equal to 0. Do you recover what like Hanselman studied in that case?
Yeah, I don't know. I mean, it's oh yeah, this.
He studied somehow the corresponding multi-module for a pair of pants across a circle, I think. You know, when he was thinking about graph manifolds in the context of ordered Floer homology.
Yeah, that's right. That's right. I think it's a little different. Like because his modules are over the bordered algebras. I think what ends up, I mean, I would maybe conjecture there's some bimodule relating A and this algebra, but I don't know. I haven't written that down yet. I mean, there's probably some relation. Probably it's not an equivalence of categories with the bordered algebra, but there's probably some relation. I haven't written that down yet, or I haven't attempted seriously to compute a module like that.
In your all this setup, I mean, you know, like in principle, I think the link surgery special sequence gives you the relative invariant of, you know, these the Floer manifolds in question. Like, are you able to kind of see that in any kind of practical way through lattice homology?
Oh, I mean, oh, you mean like there's like an inclusion on the B's or something? Is that what you mean?
Yeah, I mean, like, you know, so, you know, in Osfrad's was a sort of first paper with the plumbings, you know, like it was sort of clear that, you know, the relative invariant, you were just sort of, they were just providing all these linear functionals, which kind of just picked out the Floer homology of the boundary. And like now in this setup, it's not like, you know, you're not going to see everything in the Floer homology from the relative invariant of the Floer manifold because, like, you know, you're out of the negative definite realm. So certainly that's not going to hold. But in principle, I think the inclusion of the B's give you those maps, but I don't know if you can sort of see them in a concrete way.
Yeah, I mean, yeah, so if it's, yeah, I mean, certainly the cobordism map is the inclusion of the B's. I mean, that might, I mean, that should be the case, like you just, because there's actual maps between the links, or, I mean, Manelasco-Ojvat computed something, or they proved some version of extension of in the mapping cone formula, like inclusion of the B's as the cobordism map. So, I'm sure that still holds. Whether that's useful outside of the negative definite case, I don't know. I mean, it might not be a super interesting map if it's not negative definite, but yeah, I don't know of anything interesting to say about it. But I mean, there should be some relation like that. I don't know what you would get out of that other. I mean,
I was just thinking, I mean, maybe you can get some sort of more general rational blowdown operations. I mean, people have already studied that in this kind of geometric context, but like, you know, they didn't have access to all of the relative invariance of all plumbed manifolds. It was sort of much more limited class.
Yeah, I don't know if I have anything to say. I mean, definitely you could compute. Yeah, I'm not sure how interesting it is outside of the negative definite case, but yeah, I mean, if you definitely, it's just inclusion. It should just be inclusion of the B's. Let me just ponder this for a second. There's a map. Yeah, it would just be inclusion of the B's. Yeah, I don't know. Yeah, hopefully it's useful, but that would just be, I mean, that would be easy because, like, I mean, that follows, you have a map like this, right? And then you just have like, I mean, certainly this map, if you look at the map, would commute like inclusion of the B's. So certainly the computation follows, but yeah, I don't know, hopefully, I mean, hopefully people who know more than me could find applications of it.